Hello everyone and welcome to my video. I'm Dr. Mahdi. Today in this video I'll explain to you about chemistry reaction. First I'll give you an introduction about this reaction. In the following I'll explain to you about different types of reaction one by one with details. But the most important part for this video is different applications for chemistry. Chemistry has different applications. For example, we can use chemistry for polymerization process. Polymerization process using chemistry reaction. We can also use chemistry for bioconjugation. And also I'll explain to you how to use lithography technique. Lithography is a very new technique. How to use lithography for printing the molecule on the surface and doing chemistry reaction. And the last application for chemistry that I'll explain to you in this video is surface functionalization. We can functionalize the surface with esterification reaction or silanization or amidation reactions. And in next step, we can use chemistry to attach and connect different molecules or different functional groups on the surface. At the end of this video, if you like it, please push the like, press the subscribe button. You can also hit the bell. In this case, you will get notification whenever I publish a new video. Now let's start the video. As I already mentioned, chemistry is a new science and it refers to 2001. Here I would like to make you familiar with three scientists, with Sharpless, Kolb, and Finn. They are inventor of chemistry reaction. But what does chemistry mean? Chemistry is a class of robust chemical reaction. If you are looking for robust bond, it's better to use chemistry reaction. For example, sometimes, especially for surface functionalization and functionalization of nanoparticles, we need very robust bond. Then it means reaction or chemistry can be a very, very good candidate for surface functionalization and also functionalization of nanoparticles. Chemistry has a lot of advantages. For example, simple reaction condition for doing reaction is very simple. Compatibility with different kinds of solvent, especially water, is another advantage for chemistry reaction. Reaction rate for reaction is very high. For most of the reaction rate is very high. High yields and also high efficiency is another advantage for chemistry reaction. But I think the most important advantage is generation of minimal and non-toxic byproducts. For most of the reactions, we don't have any byproduct. And if we have any byproduct, most probably it's completely non-toxic. There are many types of reaction, but here and in this video I'm gonna explain to you about the most important ones, and I would like to start with the most popular type of reaction. I would like to start with copper catalyzed azide alkyne cycloaddition or CuAAC. It's a reaction between azide and linear alkyne in the presence of copper as a catalyst. Product will be a triazole, and product will be a 5-membered ring. We can also do this reaction in the presence of heat instead of copper. Again, reaction between azide and linear alkyne, and in this case we need to increase the temperature to 100 degrees, and we will have two isomers, 1 and 4 triazole and 1 and 5 triazole. We can use ruthenium instead of copper. Again, ruthenium can be a catalyst. In this case, we call it ruthenium alkyne azide cycloaddition. Product will be 1 and 5 triazole, but when we use copper, product will be 1 and 4 triazole. For doing CuAAC, we need to use a copper as a catalyst. Copper is toxic. Then in biological studies, we cannot use this type of reaction. Then we have a big problem with this type of reaction. Maybe you ask me, we can use this reaction in the presence of heat. When we use heat instead of copper as a catalyst, we will have two big problems. The first problem is here. When we use heat, we have to increase the temperature to 100 degrees. High temperature can have destructive effect. And also, when we use heat instead of copper, this reaction is very, very slow. Then question is here, how can we overcome to this problem? Then I suggest you to use another type of chemic reaction, and it's ester promoted azide alkyne cycloaddition, or SPAAC. What's the difference between SPAAC and CuAAC? When we replace linear alkyne with a cycloalkyne, we call it SPAAC. Again, it's a reaction between azide and alkyne, but here we have cycloalkyne. In this case, we don't need to use catalyst. I mean, we don't use copper in this type of chemic reaction. And also, this reaction is very, very fast. Then when we use cycloalkyne instead of linear alkyne, we don't need to use copper. I mean, we don't need to use catalyst. There are different types of cycloalkyne that they can participate in reaction, I mean in chemic reaction with azide group. And here you can see some commonly used cyclooctane for SPAAC. For example, we have bicyclononine or BCN. We have monofluorinated octane or MOFO. Also, we have DIFO or defluorinated octane. We have dibenzo cyclooctane. Also, we have biarylaza cyclooctane or barak, and dibenzo cyclooctane or DIPCO. Question is here, what's the difference between different types of cycloalkyne? Depends on cycloalkyne that is used in this type of chemic reaction. Definitely, reaction rate will be different. For example, when we use barak as a cycloalkyne, we will have the maximum reaction rate. But when we use MOFO, we will have the minimum reaction rate. The next example for chemical chemistry is SPANC. In this case, we replace azide with nitron. I mean SPANC or ester promoted alkyne nitron cycloaddition. It's a type of chemical reaction, and it's a reaction between cycloalkyne and nitron. For SPAC, it's a reaction between azide and cycloalkyne, but here SPANC, it's a reaction between alkyne and nitron. It's not very practical in chemistry. Then let's skip and go for the next type of chemical reaction. The next one is Thiol-ene coupling, and also we call Thiol-ene coupling alkyne hydrothiolation and Thiol-ene coupling. First, I would like to start with Thiol-ene coupling or Thiol-ene chemical reaction, Thiol-ene chemical chemistry. It's a reaction between thiol and linear alkyne. It's a two-step reaction. First, one thiol can participate in reaction with linear alkyne and triple bond turn into double bond. And in the following second thiol, in second step, second thiol will participate in reaction and double bond turn into single bond. For doing this type of chemical reaction, we need UV irradiation, and also we need photo initiator. Product will be a new type of, product will be thioether. We call the product thioether. Here you can see, here we have a triple bond, but here we have single bond because two thiol, you can see two thiol can participate in reaction. First triple bond turn into double bond, and in the presence of second thiol, double bond turn into single bond. There is another type of chemical reaction, and it's Toyol-ene coupling. Toyol-ene coupling, it's a reaction between thiol and alkene. You can see we have double bond, and in the presence of one thiol, double bond turn into single bond. I mean, it's a one-step reaction because we only need one thiol. So until now we have learned 5 different types of click reaction, and now let's go for 6th one, Thiol-ene. When we use linear alkyne, again we have to use UV irradiation and also photoinitiator for doing this type of click reaction. When we use UV irradiation, again it can have the destructive effect. I mean, in biological study, we cannot use Thiol-ene when we have linear alkyne. But again, when we replace cycloalkyne with linear alkyne, we don't need to use UV irradiation, and also we don't need to use photoinitiator. I mean, we can replace cycloalkyne with linear alkyne, and again, reaction between thiol and cycloalkyne, and product will be something like this. It can be done without UV irradiation and also without photoinitiator. When we have linear alkyne, please note, it's very, very important. When we have linear alkyne, 2 thiols can participate in a click reaction. But we have cycloalkyne, only 1 thiol can participate in reaction with alkyne. I mean, triple bond turn into double bond. Maybe you ask me, we expect to have something like this. And again, double bond turn into single bond. No, we don't have something like this. It's very important. When we have cycloalkyne, only 1 thiol can participate in reaction with alkyne, but when we have linear alkyne, definitely 2 thiol can participate in reaction. Now let's go for the next example for click chemistry, and it's Toyol and Malamite addition. Toyol and Malamite addition. We have 2 different types of Toyol and Malamite addition. It's one of them is reaction between Toyol and Malamite, and another one is reaction between Toyol and acrylate. Malamite is an unsaturated imide. You can see a double bond in the structure of Malamite. It can participate in reaction with thiol, and it will give us this product. And also in the structure of acrylate, we have a double bond. Double bond can it's a type of alkane. It can participate in reaction with thiol, and we will have this product here. You can see the new bond after doing click reaction in pink color, and also here it's new bond. The pink bond is new bond after doing click chemistry reaction. In the Malamite is unsaturated imide, and it's highly reactive to thiol. It likes to participate in reaction with thiol. But please note, it's very, very important. For doing Toyol and Malamite addition, we need a weak base, or we need a nucleophile compound. It's very important. Otherwise, we cannot have this type of click reaction. Weak base, and which one is better? Weak base or nucleophile compound? Which one should we use for doing this type of click reaction? When we use a nucleophile compound, click reaction should be faster than when we use weak base. But the thing is here, when we use nucleophile compound, reaction rate will be very slower than when we use weak base. Weak base and nucleophile compound, both of them have their advantage and disadvantage. Another type of click reaction is DielAlder cycloaddition. We can have it in 4 different shapes. DielAlder cycloaddition can be done in 4 different shapes. For all of them, product will be a 6-membered ring. You can see in all of them, product is a 6-member ring. I would like to study here this type of reaction, DielAlder cycloaddition. It's a reaction between cyclopentadiene and malamite. We can use tetrazine. Tetrazine is a 6-membered ring with 4 nitrogen. It can participate in reaction with alkane, and again we will have a 6-member ring. We can use DN. DN can participate in reaction with dienophile, and also we can use cyclodien. Cyclodien after reaction with dienophile. It's another example for DielAlder Killick reaction. Also, there is another type of Killick reaction, and we call it ring opening. Ring opening is another type of Killick reaction. Different functional group can participate in ring opening. Ring opening for epoxy. I want to give you an example for ring opening, and I would like to give you this example. Epoxy. Epoxy is something like ring. Different functional groups can participate in ring opening. And I would like to start with thiol. Thiol is a molecule that it can participate in ring opening with epoxy. And here you can see the products. But please note, for doing this reaction, we need to use, we need to use triethylamine. Otherwise, we cannot have ring opening. We can also use amine group. When we use amine group, we can have again ring opening for epoxy. Here we don't have ring anymore. But when we use amine for ring opening, we have to use catalyst. For example, we can use lithium chloride. We can use zinc perchloride. We can use bismuth as a catalyst. And also we can use azide group. Here you can see we can use azide group for doing this ring opening. But when we use azide, this reaction should be a little bit complicated. Azide first needs to turn into amine. And in this case, we have to use phosphine. We call it Staudinger reaction. Staudinger reaction means azide in the presence of epoxy and phosphine can turn into amine, and now we have amine, something like this. After that, again, we need to use catalyst. For example, we need to use bismuth, and then we will have ring opening. Polymerization process using Killick chemistry reaction. First, I would like to give you a definition of polymer and polymerization. Polymer is a large molecule which is made of many repeating subunits that we call them monomers. Polymers are created via polymerization of very small molecules which are called monomers. And also polymerization. Polymerization is a process of reacting the monomer molecules together to form polymer chain or three-dimensional networks. In this video, we would like to investigate using Killick chemistry for doing polymerization. But question is here, why Killick chemistry? Killick chemistry has a lot of advantages. Killick chemistry is a class of robust chemical reactions. With Killick chemistry, we can have very robust bonds. And also, simple reaction conditions and high yields and compatibility with different kinds of solvent are another advantages of Killick chemistry reaction. In this study, in this video, we have investigated some types of Killick reaction for doing polymerization. The first one is thiol epoxy Killick reaction. We would like to use thiol epoxy Killick reaction for polymerization. It's a reaction between epoxy and thiol. We also call it ring opening because after reaction, we don't have ring anymore. Please note, it's very, very important. If you would like to use Killick reaction for doing polymerization, you need to have at least 2 different types of monomers. Definitely final product will be copolymer, not homopolymer. If you have only one type of monomer, definitely you cannot use Killick reaction for doing polymerization. And also it's very, very important. For example, here you have 2 monomers. On the surface of one monomer you have epoxy, on the surface of another monomer you have thiol. It's very important. You need to have at least 2 epoxy groups on every monomer. I mean, on the surface of this monomer, you need to have 2 epoxy groups, and also on the surface of another monomer, you need to have at least 2 thiol groups. If you have only 1 epoxy on the surface of your monomer, or no, 1 thiol on the surface of your monomer, definitely you cannot use chemical reaction for doing polymerization. Let me give you an example. In this example, you will understand it very well. For example, we have 2 monomers. On the surface of one monomer, we have thiol. Here you can see we have 2 thiol groups. And also on the surface of another monomer, we have epoxy. Again, we have 2 epoxy groups. And after doing chemical reaction, we will have a polymer like this, and we call it reactive poly beta hydroxyl thioethers. But question is here, why reactive? Because still you can see we have some hydroxyl on the surface of polymer, and I mean they like to participate in more reactions, and after that they can participate in reaction, you can see, and we call it functionalized polymer. First we made polymer with using chemical reaction, and after that polymer participated in some more reactions, and now we have functionalized polymers. And naphthoyl chloride is an example. I mean it can participate in reaction with reactive polymer, and after that we will have functionalized polymer. Amine epoxy is another type of chemical reaction, can be used for polymerization. It's a reaction between epoxy and amine, and again we can call it ring opening, because after this type of chemical reaction we don't have ring anymore. I would like to give you an example for this type of polymerization. For example, on the surface of this monomer we have 2 epoxy groups, and again here you can see on the surface of this monomer we have 2 amine groups, and after polymerization we will have a polymer like this. I mean there are many compounds with epoxy or amine groups that they can be used for polymerization. Here I would like to give you some examples. For example, soybean oil. It's a monomer, and on this, in the structure of soybean oil, you can find 6 epoxy groups. Or no, we can use, for example, triglycidyl isocyanurate with 3 epoxy groups. And also, if you are looking for a monomer with amine group, for example, you can use diethylene threamine with 2 amine groups, or M-phenyl ediamine with 2 amine groups. There are many chemicals with epoxy or amine. Here, just wanted to give you some example. Thiol-alkyne or Thiol-ene is another type of chemical reaction, can be used for polymerization. It's a reaction between thiol and alkyne. For doing this reaction, we need UV irradiation and also photoinitiator. After doing chemical reaction, double bond turns into single bond. And now I would like to give you an example. For example, in the structure of this monomer, we have 2 double bonds, 2 alkane, and also in the structure of this monomer, we have 4 thiol groups, and after UV irradiation and photoinitiator, now we will have a polymer like this. The last example is azide alkyne polymerization. It's a type of chemical reaction. It's a reaction between azide and alkyne. For doing this type of chemical reaction, we need copper as a catalyst. That's why we call it CuAAC, copper alkyne azide cycloaddition. But the thing is here, we would like to do metal-free polymerization. We don't want to use copper as a catalyst. Then we use heat. We increase the temperature to 100 degrees. Definitely when we use copper, reaction rate should be much faster than when we use heat. But anywhere, we would like to do a metal-free polymerization. Here you can see an example. In the structure of this monomer, we have 2 alkyne, and also in the structure of this monomer, we have 2 azide groups, and after doing click reaction with increase in temperature, now we will have a polymer like this. Hope you found this video useful. If you would like to know more about click chemistry, I recommend you to study my papers that you can see list of them. All of them are about click chemistry reaction, bioconjugation using click chemistry reaction. First of all, I would like to give you a definition of bioconjugation. Bioconjugation is a chemical strategy to form a stable covalent link between two molecules, which at least one of them is biomolecule. For example, you have two molecules and you want to have a covalent bond between these two molecules. You can use a bioconjugation, but please note at least one of them should be biomolecule, and also it's possible both molecules could be biomolecules, one or two. But for this purpose, we would like to use a click chemistry reaction. But why click chemistry? Click chemistry is a class of robust chemical reaction. I mean, if you are looking for very robust bond, it's better to use a click reaction. And also, a click reaction has some more advantages. For example, simple reaction conditions, high yield, and also compatibility with different kinds of solvents, especially water is another advantage for click chemistry reaction. That's why that we want to use click chemistry for bioconjugation. In the following, I would like to give you some examples about bioconjugation, and I would like to start with nanoparticles conjugation. I mean, we would like to have some biomolecules on the surface of nanoparticles. And I already mentioned we need to when we want to have bioconjugation, we need at least one biomolecule. But here, you know, nanoparticles are not biomolecule. Definitely the second part that we want to have it on the surface of nanoparticles, they should be biomolecule. Here you can see general schematic of bioconjugation with nanoparticles. For example, we have nanoparticle. Here you can see the nanoparticle. In next step, we cover the surface of nanoparticle with dopamine acrylamide. In the structure of dopamine acrylamide, we have alkane. And now, in next step, we would like to do bioconjugation and connect some biomolecules on the surface of nanoparticle. And for this purpose, we would like to use click chemistry. Which type of click chemistry? We would like to use Thiol-ene. Thiol-ene is a type of click reaction. It's a reaction between thiol and alkane. We already we already attached alkane on the surface of a nanoparticle. In next step, we would like to connect a biomolecule. For example, we would like to connect PEG on the surface of nanoparticle. We need to find the PEG with thiol group, and after click reaction between thiol in the structure of PEG and also alkane on the surface of nanoparticle, we can functionalize a nanoparticle with PEG. And also we can attach aptamer. We can have a bioconjugation between nanoparticle and aptamer. Again, we need aptamer with thiol group, and again after click reaction, we will have aptamer on the surface of nanoparticles. Another type of bioconjugation, for example, we would like to have a protein on the surface of nanoparticle, and in this case, we can use proteins with cysteine group. Here you can see a structure of cysteine. Cysteine is the amino acid. In the structure of cysteine, we have thiol, and thiol in the structure of cysteine can participate in reaction with alkane, and after click reaction, we can have protein on the surface of nanoparticle. I mean, we have already functionalized the nanoparticle with a protein, or we have already bioconjugated a nanoparticle with protein. The second example for bioconjugation is a DNA conjugation. For example, sometimes we would like to attach something to the DNA. In this case, we call it DNA conjugation. I would like to give you an example. For example, we have DNA and we would like to attach protein on the surface of DNA. I mean, we would like to have DNA protein conjugate. Again, we would like to use click chemistry, but which type of click chemistry? CuAAC, copper alkyne azide cycloaddition. It's a reaction between azide and alkyne in the presence of copper as a catalyst. For example, we have DNA. First, we need to have alkyne modified DNA. First we need to have alkyne in the structure of DNA. In next step for protein, we need to have azide protein or azide peptide. We need to have azide in the structure of protein. You know, in the structure of protein, we have an H2 amine. We can, we need to look for a molecule with azide group and, for example, NHS ester. And after reaction between NHS ester and amine in the protein, we can connect azide to the protein. Now we have DNA with alkyne group, and also we have protein with azide group. And after Killick reaction in the presence of copper as a catalyst, we can have DNA peptide or DNA protein conjugate. And I would like to give you some more example for DNA conjugation. For example, sometimes we would like to have a fluorophore. We would like to have a fluorescent ink on the surface of DNA. Again, we need to make alkyne modified DNA. We need to have alkyne in the structure of DNA. In next step, we need to use a fluorescent ink with azide group. For example, tambroazide. In the structure of tambroazide, we have azide. Azide in the structure of fluorescent ink, and also alkyne in the structure of DNA. And after Killick reaction between azide and alkyne, now we can have DNA fluorescent ink conjugate. Or no, sometimes, for example, we would like to have a vitamin attached to the DNA. Again, we need to have alkyne modified DNA. We need to have alkyne in the structure of DNA. In next step, we can use a vitamin such as biotin with azide group. For example, we can use biotin azide. It's a structure of biotin with azide group. And again, after Killick reaction between alkyne in the structure of DNA and also azide in the structure of biotin, we can have DNA biotin conjugate. The third example for bioconjugation is protein conjugation. Sometimes we would like to attach something to a protein, and again we would like to use Killick reaction. In this case, we would like to use SPAAC, estering promoted alkyne azide cycloaddition. It's a reaction between azide and cycloalkyne, and in this case we don't need catalyst. First, we need to have azide in the structure of a protein. I already mentioned I have to have azide in the structure of protein. First we need to attach azide to the protein. And also in the structure of second biomolecule that we would like to have it attached to the protein, we need to have cycloalkyne. And after Killick reaction between cycloalkyne and also azide in the structure of protein, we can have a protein conjugation, something like this. In the following, I would like to give you some more examples for protein conjugation. For example, we have protein, and we would like to have different molecules, different biomolecules attached to protein. And first, we need to have alkyne modified protein. First we need to connect or attach a cycloalkyne to protein. In next step, for example, we would like to have protein-protein conjugation. We would like to attach protein to our protein. In this case, in the structure of second protein, we need to have azide, and azide in the structure of second protein, and also alkyne in the structure of first protein. And after Killick reaction, we can have protein-protein conjugate. Sometimes we would like to have a fluorescent protein. If you would like to have a fluorescent protein, again, you need to use bioconjugation, and you need to use a fluorescent ink. For example, tambroazide. In the structure of tambroazide, we have azide group. Tambroazide is fluorescent. And in the structure of protein, we have cycloalkyne. Again, after Killick reaction between fluorescent ink and also alkyne in a protein, we will have fluorescent protein or protein fluorescent conjugate. And sometimes we would like to have PEG attached to the protein. In this case, we need to have azide in the structure of PEG. We are looking for azide PEG, and after Killick reaction between azide in PEG and also cycloalkyne in protein, we will have a protein PEG conjugate. And the last example for bioconjugation is antibody DNA conjugation. For example, sometimes we would like to attach DNA to antibody. We can use bioconjugation. I would like to give you an example. For example, here we have antibody, and we would like to attach DNA to antibody, and again using Killick chemistry. But which type of Killick chemistry? Toyol and Michael cycloaddition. Toyol and Michael cycloaddition, it's a reaction between thiol and malamite. For example, here we have antibody, we have immunoglobulin antibody. In the structure of antibody, we have disulfide bond. First, we need to use tertiary carboxyethyl phosphine for reducing disulfide bond, and after that, we will have thiol. In the structure of DNA, we need to have malamite, and after a click reaction between thiol and also malamite, we will have antibody DNA conjugate. How to use lithography technique for printing the molecule on the surface and doing click reaction, and also protein immobilization. For doing lithography and printing the molecule on the surface, we need to use this chip. This chip is called Microchannel Cantilever. It's a very small chip, maybe 5 by 5 millimeter. And also at the end of this chip, there is a channel. This channel is very, very small, and you cannot see it with, I mean, naked eyes. And width of this channel is near 10 micron. That's why we call it Microchannel Cantilever. I mean, first you need to inject the ink, and ink will go through the channel to the surface. Channel can transfer the ink to the surface, and you can print the molecule on the surface. For doing lithography, we need to use this machine. We need to mount this chip to this machine. This machine is called NLP. Here and in this video, you can see printing the molecule on the surface. You can see ink is transferring to the surface through this channel. Width of channel is 10 micron. It means diameter for every droplet, for every dot is 10 micron. Distance between two dots is 50 micron. But a question is here, why should we use a lithography technique for printing the molecule? Lithography has some advantages. For example, you can print different molecules such as phospholipid, lipid, protein, and everything else. And with this technique, you can have very, very small droplets, in very, very small volumes, near femtoliter, 10 to the minus 18. And after printing the molecule on the surface, you can have a micro array. But here in this study, as I already mentioned in this video, we would like to use lithography for printing the molecule on the surface and doing click reaction, and also protein immobilization. First, I would like to start with a click reaction. We would like to print the molecule to the surface and do two different types of click reaction. Just an example, I have selected SPAC and Thiol-ene coupling. SPAC is estrogen promoted alkyne azide cycloaddition, and Thiol-ene and this one is Thiol-ene coupling. First, you need to cover the surface with alkyne. First you need to functionalize the surface with alkyne. You have alkyne on the surface. In next step, for doing click reaction, SPAC, it's a click reaction between alkyne, cycloalkyne, and azide. In next step, we use lithography technique. We injected tamroazide. Tamroazide is a fluorescent ink. It's red. We injected tamroazide, and we printed tamroazide on this surface. This surface contains of cycloalkyne. And we need to leave it for 1 hour. And after 1 hour, we need to wash it. With water, we wash the surface. And now you need to take a photo with fluorescent microscope, and we will have something like this. You can see the red dots on the surface. Red dots, these are, tamroazide. When we have tamroazide on the surface, it means click reaction between azide and alkyne has taken place. And click reaction was successful. And here you can also see a scale bar. A scale bar is 50 micron. Distance between two dots is 50 micron, and diameter for every dot is 10 micron. The second type of click reaction is again when you have alkyne on the surface, you can do click reaction. You can do Thiol-ene coupling. It's a reaction between thiol and alkyne. Here in this study, we use the Cy5 peg thiol. Cy5 peg thiol, it's a fluorescent ink, and we injected the Cy5 peg thiol to microchannel cantilever, and after printing on the surface, we left the sample for half an hour, and after half an hour we washed the surface, and we took a photo with fluorescent microscope. Cy5 is violet, and again you can see the violet dots. When we have violet dots, it means we have psi5 peg Thiol on the surface, and when we have psi5 peg Thiol on the surface, it means click reaction between Toyol and alkyne has taken place. I mean, click reaction was successful. If you would like to know more about click reaction and also surface functionalization, I ask you to watch the videos that I already published, and you can also find the link for them at the end of this video. We use lithography for printing the molecule and doing click reaction, and here we would like to do lithography for immobilization of protein. Here we have selected the streptovidin. I mean, we would like to immobilize streptovidin on the surface with the help of lithography and printing the molecule. Again, we use the SPAC click reaction. We have alkyne on the surface. I mean, we have cycloalkyne on the surface. And here we use biotin peg azide. Here you can see a structure of biotin peg azide. Biotin peg azide is not fluorescent. And again, we injected a biotin peg azide to this chip here, and after printing the biotin azide on the surface, we left the surface for 1 hour, and after that we washed the sample. I mean, we washed the surface, and after washing we covered the surface with FITC streptovidin. It's a type of fluorescent streptovidin. We covered the surface with this streptovidin, and we left the surface in a dark room, in a dark place with room temperature, and after 1 hour we washed the surface. And after washing, again we took a photo with fluorescent microscope, and here you can see the photo. You can see the green dots. Green dots are streptovidin. When we have streptovidin on the surface, it means we have biotin on the surface, because biotin has affinity with streptovidin, and every streptovidin can be connected to 4 biotins. I mean, every streptovidin has 4 binding sites for connection to biotin. And here you can see the green dots. When we have green dots, it means we have a streptovidin on the surface, and when we have a streptovidin on the surface, it means we have biotin. And when we have biotin, it means click reaction has taken place between biotin azide and cycloalkyne. You can see immobilization of streptovidin with lithography technique. You have to immobilize the streptovidin as a protein on the surface. There are different ways, different methods for immobilization of protein on the surface. For example, we can use adsorption, we can use ionic bond or covalent bond, and also we can use entrapment method for immobilization of protein on the surface. But in this video, we will learn a different way, a different method for immobilization of streptovidin on the surface. Streptovidin is a protein and it has affinity with biotin. Biotin is vitamin B7. Every streptovidin has 4 binding sites for connection to biotin. I mean, 4 biotins can be connected to 1 streptovidin. Binding of biotin to streptovidin is a non-covalent interaction, and I should tell you it's the strongest non-covalent interaction in the nature. Here, if we would like to cover the surface with streptovidin, first we need to cover the surface with biotin. I mean, first we need to immobilize biotin on the surface. I mean, first we need to have biotin terminated surface. There are different ways or methods for functionalization of surface with biotin with different efficiency, but it's better to find a method with high efficiency. In this case, we can be sure we have enough biotin on the surface, because when we have enough biotin on the surface, in this case, we will have enough streptovidin on the surface, and it means immobilization has been successful. Here and in this slide, you can see the structure of biotin. In the structure of biotin, we have carboxylic acid group. Suppose we want to immobilize biotin on the surface. Surface, for example, is glass. First, we need to use plasma treatment for 2 minutes. In this case, we will have hydroxyl on the surface. After that, with esterification reaction between hydroxyl on the surface and carboxylic acid group in the structure of biotin, we can cover the surface with biotin. I mean, we can immobilize biotin on the surface. But esterification reaction is not very robust, and in this case, we cannot be sure that we have a lot of biotin on the surface. And also, biotin is not stable. That's why I suggest you to use click chemistry reaction. When we use click chemistry, in this case, we will have very robust bond. I mean, with very robust bond, we can connect biotin on the surface. In this case, we can make sure biotin biotin is stable, and also we can be sure that we have enough biotin on the surface. If you would like to know more about chemistry and also surface functionalization, I would kindly ask you to watch the videos that I already published, and also you can find the link for them at the end of this video. Now let's go step by step with functionalization of surface with biotin, or immobilization of surface with biotin. Suppose surface is glass. We have glass. We would like to cover the surface of glass with biotin. First, we use plasma treatment for 2 minutes, and after that, we will have hydroxyl on the surface. After esterification reaction, we can cover the surface with alkyne. Or no, sometimes we are looking for thiol on the surface, we can use thiol-ionization, and after thiol-ionization, we will have thiol on the surface. And also, again, we can use thiol-ionization, and in this case, we can cover the surface with epoxy. Biotin can be connected with different functional groups. I mean, different functional groups such as thiol, amine, azide, alkyne, everything can be connected to biotin. For example, when we have alkyne on the surface, we can use biotin thiol. I mean, we can use biotin with thiol. I mean, functional group is thiol. And after Killick reaction, after thiol and Killick reaction, we will have biotin on the surface. Now we have immobilized biotin on the surface. This biotin has been connected strongly to the surface, and also in this case, biotin is very stable. Or no, sometimes in the structure of biotin, we have azide. When we have azide, we can use ester promoted alkyne azide cycloaddition. In this case, after Killick reaction, we can cover the surface with biotin. When we have thiol on the surface, we can use biotin malamite, and after Killick reaction, cover the surface with biotin. Or no, for example, we can use biotin dipco. Biotin dipco, it means biotin has been connected to cycloalkyne, and after Killick reaction, we will have biotin on the surface. When we have epoxy on the surface, again, we can use ring opening or Killick reaction. I mean, we can use biotin amine. In this case, we will have biotin on the surface. Or no, we can use biotin with thiol group. Again, in this case, we have biotin on the surface. In this case, we have prepared 6 different surfaces contain of biotin. This biotin is very stable, and also in this case, we will have a lot of biotins on the surface. In next step, here you can see we have prepared biotin terminated surface. I mean, we have immobilized biotin on the surface. But we are gonna immobilize streptavidin on the surface. That's why in next step, we cover all of the surface, this surface with streptavidin and leave it in room temperature for 1 hour. When we leave it for 1 hour in room temperature, definitely we will have non-covalent interaction between biotin and streptavidin. And after 1 hour and washing, we will have 1 layer of streptavidin on the surface. I mean, we have immobilized streptavidin on the surface. Sometimes maybe you want to make a sandwich of streptavidin. In this case, again, we can cover the surface with pure biotin, but in this video, we don't want to make sandwich, just we want to immobilize streptavidin on the surface. And first we use chemistry, we cover the surface with biotin, and then in the following, with non-covalent interaction, we cover or we immobilize the surface with strepta. Now to modify or functionalize the surface, I mean, sometimes we are looking for some special functional groups on the surface. I mean, some functional groups such as amine, thiol, azide, alkyne, or anything else. In this video, we will learn how to cover or modify or functionalize the surface with these functional groups. And I would like to introduce you 2 different types of surface functionalization or surface modification: esterification and thiol-inization. First, I would like to start with esterification reaction. Esterification reaction is a reaction between carboxylic acid group and the hydroxyl group, and product will be an ester. That's why we call this reaction esterification reaction. We want to use esterification reaction for surface functionalization or surface modification. Here you can see the general schematic of reaction. We have a surface. Surface can be glass, it can be diamond, gold, silicone, and anything else. For doing esterification reaction, we need to have hydroxyl on the surface. If you want to have hydroxyl on the surface, you have two options. First, you can use oxygen plasma. When you use oxygen plasma for only 2 minutes, you will have a lot of hydroxyl on the surface. Or you can use Piranha solution. Piranha solution is a solution, it's a mixture of 100% concentrated sulfuric acid and hydrogen peroxide. Mixture ratio is 3:1. Piranha solution is a very, very dangerous solution, and you need to leave your substrate, your surface in this solution for 1 hour, and after that you need to wash it. This solution is very dangerous. That's why I don't suggest you to use Piranha solution if you want to have hydroxyl on the surface, and it's better to use oxygen plasma. It takes only 2 minutes, and after 2 minutes you will have a lot of hydroxyl on the surface. Now you have hydroxyl on the surface, and you want to, with with esterification reaction, you want to cover the surface with this compound. You need to leave substrate in this compound for 24 hours, and also you need two catalysts, DCC, the dicyclohexyl carbonamide, and also DMAP, dimethyl aminopyridine. You need to leave your substrate in this solution for 24 hours, and after 24 hours and washing, you will have your compound on the surface. And also, if you want to make sure you have enough molecule on the surface, it's better to do this reaction. It's better to do esterification reaction in the presence of nitrogen atmosphere. Now, after esterification, after reaction between carboxylic acid group and hydroxyl, now you have your compound. You have your compound on the surface. Here you can see the R. R can be everything. R can be thiol, it can be azide, it can be alkyne, amine, and anything else. Now, in the following, I would like to introduce you surface functionalization with different functional groups. For example, sometimes you need to have thiol on the surface. It's better to use this compound. This compound is thioglycolic acid. When you use thioglycolic acid and after esterification reaction, on the surface you will have a lot of thiol. You have thiol terminated surface. Or no, sometimes you are looking for benzene on the surface. When you are looking for benzene on the surface, you can use this compound, and again after esterification reaction with your substrate, with your surface, you will have benzene on the surface. Here you can see the structure of glycine amino acid. Glycine is an amino acid. There are 20 different types of amino acid in the structure of all of the amino acid. There is carboxylic acid group. If you would like to cover the surface with amino acid, you can use esterification reaction. After esterification reaction, you will have your amino acid on the surface. You will have your favorite amino acid on the surface. Sometimes you are looking for NHS or N-hydroxysuccinimide on the surface because you would like to do ester amine reaction. You can use this compound. Again, in this compound there is carboxylic acid group, and after esterification reaction you will have NHS on the surface, and after that you can do ester amine reaction. Sometimes you would like to use surface functionalization for doing some types of click reaction. For example, we have click reaction, it's between alkyne and thiol, and also there is another type of click reaction, it's between alkyne and azide. Here in the structure of defluorinated cyclooctane, you can see carboxylic acid group. When you cover the surface with esterification, after doing esterification reaction, you cover your surface with this alkyne, and in this next step you can do click reaction. Or no, sometimes we can use this compound. In the structure of this compound, we have carboxylic acid group, and again after esterification reaction, we will have azide on the surface. Now you have azide on the surface, you can do click reaction with cycloalkyne or linear alkyne. Now I would like to start with a second method for surface functionalization, and it's thiol-ionization reaction. Thiol-ionization reaction is a very cheap and effective method, and also it's suitable for modification of surfaces that we have a lot of hydroxyl on the surface of them. For example, if you have a surface with a lot of hydroxyl, it's better to do thiol-ionization reaction. Here you can see a general schematic of thiol-ionization. Again, you need to have hydroxyl on the surface. I mean, first you need to use oxygen plasma again for 2 minutes, and after that you will have a lot of hydroxyl on the surface. You have hydroxyl on your surface, you need to leave your surface in a solution with a desired compound, I mean with a compound containing of silane group, and I think it's enough to leave it for 3 hours, and after 3 hours and after washing, now you can have your compound on the surface, and here again you can see R. You can change the R according, I don't know, for example, if you are looking for Thiol, you can replace R with Thiol. If you are looking for amine, you can replace it with NH2 amine and anything else. Here you can see surface functionalization with different functional groups. For example, if you would like to do silanization, and if you would like to have thiol on the surface, it's better to use MPTMS, mercaptopropyl trimethoxysilane. But please note, mercaptopropyl trimethoxysilane, it's a liquid shape, and you don't need to use pure mercaptopropyl trimethoxysilane. Sometimes you need to make a solution 1% or 2% in Thiol-ene. I mean 1 milliliter MPTMS or 2 milliliter MPTMS in 100 milliliter Thiol-ene, and you need to leave your substrate, and after 3 hours washing you will have this compound on your surface. Sometimes you are looking for amine on your surface, you can use aminopropyl trimethoxysilane. I mean after silanization you will have amine on the surface, and you can also use glycid oxypropyl trimethoxysilane. In this case you will have epoxy on the surface, and after that you can do different types of ring opening reaction. If you would like to do ester amine reaction, you can use this compound, silane PEG NHS, and again after leaving the substrate in this solution for 3 hours, you will have NHS on your surface. 2 different types of amidation reaction for surface functionalization or surface modification. As I already mentioned, we will learn about 2 different types of amidation reaction. The first one is NHS or N-hydroxysuccinamide ester amine reaction. It's a reaction between a primary amine and also NHS ester. Product will be an amide. That's why we call this reaction amidation reaction. Here and in this slide, you can see general schematic for doing this reaction. First, we need to cover the surface of substrate with amine. Substrate can be everything. Substrate can be gold, can be silicone, glass, diamond, and everything else. And for this purpose, I mean, we need to cover the surface with ammonia, and we can use plasma. We can use ammonia plasma, and after 2 minutes, we will have a lot of amine on the surface. After that, we need to dissolve our compound in desired solvent and immerse the substrate in this solution for half an hour, maximum 1 hour. pH is very, very important. Please note, pH should be between 7 to 9, and after half an hour or 1 hour, we can wash the substrate. Now we have our compound on the surface. And here you can see the R can be different. We can change the R. I mean, R can be different functional groups. For example, R can be thiol. I mean, after doing NHS ester reaction, we can have thiol on the surface. Sometimes we would like to cover the surface or with a vitamin. Here you can see vitamin B7 or biotin. I mean, sometimes we would like to cover the surface with biotin, vitamin B7. Again, in this case, we can use NHS amine reaction. After reaction, we will have biotin on the surface. Sometimes we would like to do chemical reaction on the surface. I mean, we can use NHS amine reaction to cover the surface with alkyne or malamite. When we cover the surface with alkyne, we can do Thiol-ene or SPAAC, estrogen promoted alkyne azide cycloaddition. I mean, 2 different types of chemical reaction. And also when we covered after doing NHS amine reaction, and when we cover the surface with malamite, we can do Toyol and Malamite cycloaddition. That it's another type of chemical reaction. The second type of amidation reaction is EDC coupling reaction. EDC coupling reaction, again, it's a reaction between carboxylic acid group and a primary amine, product will be an amide. That's why again we call this reaction amidation reaction. But please note, we need to use EDC or ethyl dimethyl aminopropyl carbonamide. It's very important. We need to use this catalyst to do this reaction. Again, in the presence of this catalyst, this reaction can be done very fast. I mean, in 1 hour, this reaction can be done. Here and in this slide, you can see general schematic for doing this reaction. Again, we need to cover the surface with amine. For this purpose, we need to use a plasma, and we need to use ammonia plasma. And after again 2 minutes, we will have a lot of amine on the surface. In next step, we need to dissolve our compound in desired solvent and immerse the substrate in this solution and leave it for 1 hour. And after washing, now we will have our compound on the surface. Again, we can change the R can be different functional groups. For example, R can be thiol. After this reaction between carboxylic acid group and amine on the surface, we will have thiol on the surface. We will have thiol terminated surface. Sometimes we need to have benzene on the surface. Again, after doing this reaction, EDC coupling reaction, we will have benzene on the surface. Here you can see a structure of a glycine. Glycine is an amino acid. In the structure of all of the amino acid, there is carboxylic acid group. We can use this reaction to cover the surface with different types of amino acid. Depends. For example, if you want to cover the surface with glycine, you can use this reaction. After reaction between carboxylic acid group and amine on your surface, we will have amine on your substrate. And also, again, you can use this type of amidation reaction for doing click reaction. For example, here you can see difluorinated cyclooctane, and this side there is carboxylic acid group. And after doing reaction, we can have alkyne, and then in the following we can do click reaction. And now, and in this slide, I would like to investigate gold as an example. For gold, it's a little bit different. When we have gold and we want to functionalize gold, we don't need to use any functional group on the surface. We don't need to have hydroxyl or NH2 amine on the surface. But please note, we need to have thiol in our compound. When we have thiol in the structure of our compound, we can functionalize gold without any functional group on the surface. Let me give you an example. For example, we have this compound. In one side we have NHS, and this side we have thiol. Thiol without any functional group on the surface of gold, it can be connected to the surface of gold. We don't need to have anything on the surface of gold. Or for example, here again you can see another compound with a carboxylic acid group and thiol. If you would like to have carboxylic acid group on the surface, and as your compound has thiol, you can functionalize gold without any functional group on the surface. This compound can be connected to the surface from this side, from thiol side, and now after that you will have carboxylic acid group on the surface. Or for example, here you can see a structure of histamine. Histamine has NH2 in one side, and other side it has thiol. Thiol can be connected directly to the surface of gold, and other side we will have NH2 or amine. It means we have amine terminated surface. So, thanks for watching my video. I hope it was useful for you. If you like my video, please push the like, press the subscribe button, and share it with your friends. And also, you can hit the bell. In this case, you will get notification whenever I publish and upload a new video. Thanks again. And at the end, please don't forget, life is short and enjoy it. Thank you so much. Bye.